First of all, Patil Sahab, I am extremely sorry that I not able to send that details yesterday because I was quite busy. So anyway, now I am trying to clear it, and I feel um, this video will be sufficient to understand what we are going to do. First, I will go to the power circuit. That is the main thing. So just you see, this is the power circuit. So it will be consisting of several H-bridge cells. So this entire thing called a H-bridge or power cell. So even though it's just a brief concept, means this is to understand the topology. The detailed thing it will take to understand the in detail we will discuss later on. So when we will meet, that time we will explain the things in detail. So this is just to have an idea. So here you see it's a simple diode rectifier which will converting the AC to DC. Then this is the filter to reduce the ripple, and after that this is the simple H bridge. So in the positive half, this P1 and P2 switches will be triggered, and for the negative half, N1 and N2 switch will be triggered. So this is the basic one cell. And like that, you see here I have like that 5 cells I have introduced to meet the my phase voltage actually. So to meet my phase voltage, 5 cell. And how I have introduced 5 cell, this is just to have an idea, but you can reduce the number of cells based on the availability of the IGBTs and its rating. Diode side absolutely no problem, you will get the diodes, but the IGBT rating it's limited. Very few manufacturers in the world will manufacture. So now let us see that how I have arrived it. You see, my motor voltage, the motor phase voltage, I need, the line voltage is 3150 volt RMS, 3150. So this is, the motor is star connected. So my phase voltage will be this line voltage by √3. That means 3150 divided by √3, which will come around 1819 volt, 1819 volt. Now that is my RMS voltage. So DC side better to calculate in peak. So now if my AC voltage is 1819 and convert into peak, you have to multiply by √2. So it will come around 2072 volt, and as I have divided by 5, so it will come around 514 volt. That is my DC. So again in RMS, if you divide by √2, it will come 363. You see, that's why I have written each IGBT rating should be 364 RMS, and my line current is 804 amps. That's why I have. So this can be reduced. Say so my total RMS voltage is coming per phase, it is 1819 volt. Suppose I got some IGBT which having which can carry 700 amps. So you see, I can complete the things within 3 cells, like that, 3 cells in each phase, and that is 9 cell for 3 phase. So this things is entirely depend on the the number of cells. It will entirely depend on the IGBT rating. Okay, so I feel this is this IGBT selection and how to this is clear. Now what is the input of the rectifier? So now for this configuration, say I need 364 volt RMS, so you multiply by √2. So this is my VDC. This VDC I want actually. So to get this VDC, and now let us find out how much AC input I need. So that is into pi. So this is pi divided by 3 divided by √3. So 311 volt, that is my phase voltage. That is my phase voltage peak. That is my phase voltage. One second, I will calculate. So this is my RMS is 364, my DC RMS is 364 into √2. This is coming this much. So into pi divided by 3 divided by √3. Yes, so 311 is the 311 will be my input phase voltage peak. So RMS, again I have to divide it by √2. Again I have to divide by √2. So it is, this is this one, and again this is my line phase voltage, so again multiply by √3. So nearly 381 volt will be the 381 volt will be the input of the this one, the rectifier. Okay, so my input side is availability is 6.6 kV. So now you have to get a transformer whose input is 6.6 kV line voltage, line RMS, and output is 381, and my line current is 804. So into, this is my line voltage, this is my line voltage RMS, into 804, this is this one, so 306 into √3 VLIL. So nearly it will come 531 kV. 531 kVA one transformer. This is the transformer requirement, because it is drawing that much current. So around this is the this side transformer rating. So like that, 530 kVA, like the transformer for this one, we require 15 numbers, 15. So this is nothing but, this is the power circuit explanation about power circuit, and the architecture I think you understood. Absolutely, there is no problem. And now handling with this low voltage and current is absolutely not a problem. Okay, now I will go to the control circuit. So in control circuit also, it's already a proven thing. You need not to do any R&D. Already microchip, this TSP, people have implemented, and nothing to do, entire thing is given here. Okay, so you see, this is my motor. Actually here is my all, this is my that configuration whatever I have shown you. It's a multi-level sine PWM. So from here you have to take the feedback, the current feedback you have to take, and then this is a three-phase current. Better to, for my analysis, it is always advisable to convert the three-phase to two-phase. So it is three-phase, here it is two-phase. Now this I have to find out in the rotor side, so you need theta. So this is a model through which the theta is calculated, and I'll tell you how this thing. Then once you able to know the theta, then you will getting ID and IQ, and this is your speed reference. Okay, in at what speed I want to rotate the machine, and feedback I am taking from the incremental encoder. It's generating the error signal. So then this is my PI. It is properly tuned. If you are able to tune properly, it will give you the torque reference, that means quadrature axis current reference. This quadrature axis current reference and actual quadrature axis current reference, it is compared, and you are generating, that is error. And after again one controller, this is PI controller, you are getting the quadrature axis reference voltage. And similarly to generating the flux, this is the direct axis current. You are comparing with the actual direct axis current, generating the error. Then you are using API regulator, and you are generating the direct axis voltage reference. And again, this is the rotor side, so you are converting into stator side. You need theta. So then you are generating the V alpha and V beta two phase, and now it is very much easy to generate the modulating signal. So from that, basically this is your modulating signal. This is the modulating phasor. This is the horizontal component, this is the vertical component. Now you can compare this value with a high frequency carrier, and you can generate the PWM pulse to trigger the bridges as I shown in the power circuit. And these are the things. It's very simple mathematics how to convert to alpha to DQ, then this three phase to two phase, and this is, there is inside a current model. Here you have seen a current model. This is the current model. So its output is theta, so input is ID, IQ and speed, and your output is theta. So this is how to do it. This is the if you really need to understand that how it is coming, I will explain you, but this is simple mathematical equation. And this is the abbreviation of what are the things it's written. Okay, this is the abbreviation of the symbol, and this is the thing. So this is the things needed to be done. And now I will tell you one thing. Here you need not to do any detail engineering. If you are feeling, if you think that okay, this entire the detail engineering is to be done by you, you can do, but I will give you some good solution so that we can avoid the time delay. The entire rack as a plug and play system will be given by semicron. So this diode, IGBT, heatsink, capacitor, everything, it will come as a black box and with a driver. Just you have to give the microcontroller triggering pulse, it will work. This form will be given by, that will be supplied by semicron. It's one of the famous manufacturer of IGBT and this power switches, you might be aware. Otherwise there are in that whatever voltage, if you split up, plenty of but one thing, you have to choose the IGBTs such a way at least the switching frequency will be more than 4 to 5 kilohertz. Then your output harmonic and the ripple will reduce, and you need not to use any filter. Actually the same drive I have developed with a 3-level switching. This is not this type of H bridge. It's simple, 4 switches. It's a 3-level switching in it's like 4 switches in a leg, like the 3 legs are there. So as you know, the voltage is coming nearly so this is for 3-level switching. I have made it nearly 5200 volt, because it's a single leg. So 5200 volt, if I am able to switch in a single, it is your switching frequency. My switching frequency is restricted to 750 hertz. Now you know 750 hertz is a very low frequency, and for that I was forced to use some filter at the output, passive filters, RLC filters. So you know, being non-linear in nature, it's the introducing of any non-linear passive device in a high frequency switching system. It's nothing but I am inserting some instability. So this is due to that several problems is arising. So to avoid that, now I am reducing the current rating of the power rating of the switches, and now it is readily available. Plenty of suppliers available in the market, like Semicron, Infineon, Mitsubishi, Toshiba, Hitachi, Fuji, Fairchild. Plenty of people are available, but among these I'll suggest you to use first choice should be Semicron. It's a very user friendly, and it will not give you any trouble. And suppose if you are not comfortable with Semicron, then you go to Infineon, the dealers available in India, and they are also very good. You will get it from, just 1 minute. And that is available in Infineon, that this one Ariant Electrical, Delhi, they are the authorized people. They are also giving the entire solution. So this is all about the things. You just discuss with your team and let us confirm that whether it can be done or not. If it is, you are assuring that it can be done, then I can come anytime and we can discuss in details, and we will plan how to proceed further. Thank you very much.